Welcome to The Explainer. Ever wonder how big companies seem to predict the future? Well, today we're going to pull back the curtain on one of the tools they use to do just that, linear regression. And I know it sounds super technical, but trust me, by the end of this, you'll see it's actually a pretty simple and crazy powerful idea. So let's start with a problem that basically every business on the planet faces. How do you forecast what's coming next? We're talking about sales, customer behavior, market prices. Being able to predict this stuff accurately is a huge, huge advantage. To make this all feel a bit more real, let's follow the story of a manager. We'll call him Winard. Winard's goal is super straightforward. He wants to figure out how to sell more stuff. He has a hunch that advertising is the answer, but a hunch isn't good enough. He needs to prove it with data. So he decides to run a little experiment. He takes his advertising budget and splits it across 3 different channels: social media, good old-fashioned TV, and, of course, newspaper ads. He wants to see how each one actually moves the needle. And as this experiment gets going, he's carefully writing everything down. What you're looking at here is a little snapshot of his results, how much he spent in each bucket, and the sales that came out the other end. This data, right here, is the raw fuel for our entire prediction machine. Okay, so now Winard's facing the classic challenge. He's done with just guessing. He needs a model, right? A system that can take any new budget he comes up with and give him a solid prediction of what his sales are actually going to be. Winard's a practical guy, so he starts with the simplest, most logical idea he can think of. He just wants to whip up a quick and easy equation to figure out what's going on. His first instinct is, well, maybe sales are just all the ad spending added together. Makes sense, right? But the second he checks it against his actual data, the whole idea just falls apart. Look at that first row. 200 plus 300 plus 400, that's 900. But he made 1,000 in sales. The math just flat out doesn't work. So what went wrong? I mean, the logic seemed totally fine, but reality told a different story. And this little failure is what leads us to the big aha moment that's really at the heart of all of this. Here's the fatal flaw in his thinking. When Winard just added the numbers, he was making a huge secret assumption that $1 spent on TV has the exact same punch as $1 spent on a newspaper. But we all know that's not how the world works. It's just like a team project, right? Some people do a ton of the work and have a massive impact, and others, well, not so much. To put it in math terms, his simple little formula was secretly multiplying each ad budget by 1. It was giving them all an equal weight, an equal level of importance. And that right there is why it all fell apart. So to fix this, we need a smarter equation. We need one that can actually learn from the data and figure out the real impact of each channel. And this is where 2 super important new ideas come in: weights and bias. First up, let's talk about weights. Sometimes they're called coefficients. You can just think of these as importance scores. So if TV ads get a high weight, it means they're really effective at driving sales. If newspapers get a low weight, it means they have less of an impact. Simple as that. But hang on, there's one more piece to this puzzle. What would happen if Winard just stopped all advertising, completely shut it off? Would his sales really drop to 0? Probably not, right? You've still got things like brand loyalty and people just telling their friends. And we have a way to account for that. It's called a bias, or sometimes an intercept. It's just a baseline number. It's the sales you'd expect to get even if you spent absolutely nothing on ads. It's our starting point. Okay, let's put it all together now. Our new, much smarter equation looks like this. Sales equals the TV budget times its own special weight, plus the social budget times its weight, plus the newspaper budget times its weight, and then at the very end, we just add that baseline bias. Now, if this is giving you flashbacks to high school math, it should. This is just a supercharged version of the classic y equals mx plus b line equation. So we've got the perfect formula now. But what are the right numbers for all those weights and that bias? That is the real mission of the machine learning model. Its entire job is to look at all that data and find the perfect set of numbers to plug into this equation. So how does a machine even find these perfect numbers? Well, it learns through a really simple but powerful loop. First, it just takes a wild guess. Then, it compares its own prediction to the actual sales data to see how wrong it was. Then, and this is the clever part, it slightly adjusts its weights and bias to try and make a better guess next time. It does this over and over, thousands of times, getting a tiny bit less wrong with every single step, until its predictions are as good as they can possibly be.
Now, there's a really cool way to visualize what the model is actually doing here. If you were to take all of its predictions, all the answers it gets from its fancy equation, and plot them on a graph, they would form a perfect single straight line.
So you can kind of picture it like this. The real-world data that Weinert collected is like a bunch of dots scattered on a chart. The model's job is to take a ruler and draw one single straight line that best represents all of those dots. And what makes it the best possible line? Well, it's the line that gets as close as possible to all of those real data points at the same time. The model is trying to find the one line that minimizes the total distance. You can think of it as the total error between its predictions and what actually happened in reality.
And here is where all comes together beautifully. Those ideas we talked about, weights and bias, they have very specific jobs when it comes to drawing our line. The weights control the slope, the steepness or tilt of the line, and the bias acts like an elevator, just shifting the entire line up or down the graph until it finds the perfect starting position. So to wrap this all up, let's just quickly hit the most important takeaways. Linear regression is all about predicting a number like sales. It does this by giving an importance weight to every piece of information you give it. It also adds a baseline bias as a starting point. And the whole goal of the model is to find the perfect weights and bias that draw the best fit line right through the middle of all your real data. Now, we used Weinert's sales problem to figure all this out, but this simple, elegant idea of finding the best line is unbelievably powerful. It's the same core idea used to predict everything from housing prices and stock market trends all the way to weather patterns, which really makes you wonder what other really complex problems out there could be simplified if we could just find the right line.